Hello and welcome back. What does a limit really mean? Let's go back to our visual understanding of what limits mean. So here we have the graph of a function. It just happens to be a line. And we're going to focus on the x value x naught. So from the picture we can say that the limit as x approaches x naught of f of x, if this is f of x here, is equal to L. And the reason for that we gave was if we look at x values that are approaching x naught from the left, the y values as x gets closer to x naught from the left, the y values get closer and closer to L. And similarly, as x approaches x naught from the right side, the y values also get closer and closer to L. Now for the limit to exist, we have to be able to get as close to L as we like. Now this closeness to L is represented by what we're going to call epsilon. Epsilon is a Greek letter and it just happens to represent a closeness to L. So here's a picture of what it looks like when epsilon equals 2. Here's 2 away from L. So if we want to make it so that our function values are within 2 of L, of the limit L, well, we're going to have to choose x values that are close to x naught, and we can do that. We can respond to this epsilon challenge, we want to be this close to L, with a closeness to x naught that's going to get us that challenge, that's going to rise to that challenge. So here's what it looks like. If we have a delta of, in this case, 0.7, so there's our interval around x naught of delta, so this is like the x values that are delta close to x naught. So all those x values in that interval, if you plug them all into the function, then the y values that you get are going to be within epsilon of L. They're going to be epsilon close to L. You can test them out. So like you can test out any of these x values inside of this delta kind of tube. And if you pick any x value in there, the y values will all fit inside the epsilon tube. So being delta close to x naught is going to imply epsilon closeness to L. But if we want the limit to exist, then what we want to do is be able to respond to this challenge no matter how small epsilon is. So suppose we take epsilon and we shrink it. Let's make it now 1. Okay, so we're shrinking our epsilon tube. Well, now a delta of 0.7 is no longer going to do it for us. Delta of 0.7, unfortunately, if we pick some x values that are close to those boundaries, they're not going to quite fit within the epsilon tube now, because epsilon is smaller. So here you can see an x value such that when we plug it, it's delta close to x naught, but when we plug it into our function, the y value is now not epsilon close to L. It's not as close as we want it to be to L. But we can respond to this epsilon challenge here of 1 by a smaller delta response. We can make delta 0.4, for example. Now, as long as we stay inside this delta interval, right, this delta interval here, then all of the y values that we get are going to be within epsilon of L. Now, if you can do this for any epsilon challenge, for any epsilon, as small as you'd like it to be, you can make epsilon be 0.0000001. You want to be that close to the limit L. If you can always respond with a delta response, so a delta that's small enough so that all of the x values that are within delta of x naught, if you plug them all into the function, you're going to get y values that are within epsilon of the limit L. Then we would say that the limit as x approaches x naught of our function is equal to L. That will prove that that limit is the case. Okay. So just to run through this one more time though, if we had chosen a smaller epsilon, we would want to make delta even smaller. And if we had chosen a smaller epsilon, we can choose delta even smaller. so that we can get as close as we like to this limit L by picking x values that are close enough to the limit to x naught. Therefore, the limit as x approaches x naught is equal to L in this case. So if we switch over to the notes, we can see the picture of the epsilon challenge on the left and the delta response on the right. Again, this green area is just all the function values, the y values of the function falling inside of that epsilon tube. In other words, all those y values are epsilon close to L. Now the formal definition is down below. It says, let f be defined on an open interval about x naught, except possibly at x naught itself. Remember, with limits, we don't care what happens at x equals x naught. We just care what happens as we get close to x naught. So there could be a hole there at x naught for all we care. So we say that the limit of f of x as x approaches x naught is the number L, and we write the limit as x approaches x naught of f of x is equal to L. That's our familiar limit notation. If for every epsilon greater than 0, here I'm going to write out epsilon, and this is the challenge. So for every epsilon challenge, we'll say, greater than 0, so every positive number, positive distance you want to be away from this limit L, if there exists a corresponding number, delta, right, delta, this is the response, it's going to rise to the challenge. There always exists a corresponding number delta greater than 0, so positive delta, such that for all x, delta closeness to x naught implies epsilon closeness to L, then we can say that this limit as x approaches x naught of f of x is equal to L. So this is where that previous video giving you the foundations for understanding that the absolute value of x minus x naught really means the distance between your x values and x naught. So this is saying all of the x values that are within delta of x naught. In fact, this was the last part of page number 1 that we showed in the picture. On our interval, it looks like this. On our x-axis, it looks like this, and that's exactly how we drew it in the previous page. Now, we didn't draw the distance between f of x and L, which is going to be is less than epsilon, which is going to be this epsilon interval about L. But basically, again, this is saying that if for every epsilon challenge there exists a corresponding delta response, so some number, and delta is going to have to get smaller the smaller epsilon is, such that for all x being delta close to x naught, so delta close to x naught implies being epsilon close to L, so this is the epsilon closeness to L. Here are all our function values, f of x, and they're epsilon close to L, they're within the epsilon of L. Then this limit exists. And by the way, the right arrow there with the double lines, this means implies, so you can think an if then. So for all x, if x is within delta of x naught, then f of x is within epsilon of L. All right. So before we get into that first example, I'm going to end this video and see you in the next video. Thanks for watching.